Hello there. Welcome and thank you for joining us today. We are going to take a comprehensive technical deep dive into DiFi, which stands for the Digital Intermediate Frequency Interoperability Standard, and explore its transformative impact on satellite communications. My name is Arpad, and I'm part of Lasting Software, a company set on building advanced solutions and tools that bridge the gap between end-to-end theory and implementation, between radio channel theory and real-world signal testing. Today, we'll start by looking at the historical context and technological pressures that led to the creation of DiFi, break down the architecture and implementation of the protocol, examine how it's evolving through upcoming versions, and finally discuss how Celeos, our software-defined channel emulator, which you know quite well by now, is integrating with the standard. Overall intent is to go beyond marketing level overviews. This session is designed to be instructive, detailed, and directly applicable to engineering teams working on the future of RF systems. So, without any further ado, let's jump right in. Historically, satellite systems have relied on analog intermediate frequency connections to transport RF signals between key components, such as modems, converters, baseband units, and test equipment. But analog cabling introduces limitation in range, noise resilience, configurability, and integration. As satellite infrastructure evolves, with trends such as software-defined payloads, virtualized ground segments, and disaggregated architectures, the case for replacing analog transport with digital has become undeniable. Digital intermediate frequency carried over Ethernet infrastructure opens the door to software-defined connectivity, centralized or remote testing, and cloud-based RF processing. But these gains are only possible if there's a shared protocol, a common language that ensures low latency, phase-aligned, and interoperable transport, basically everything that DiFi addresses today. But what is DiFi? Well, DiFi is a network protocol specification that defines how digital intermediate frequency samples should be packaged, transmitted, and interpreted across IP-based transport layers, usually Ethernet. Developed by a group of vendors and standardization advocates, DiFi offers an interoperable solution for exchanging IQ samples and timing data with the precision needed for RF applications. It uses UDP to ensure lightweight transmission with the minimal overhead, while introducing mechanisms like sequence numbers, sample clocks, and precise timestamps to support deterministic operation. Importantly, DiFi is designed not only for hardware systems, but for software-defined radio chain and virtual components as well, making it basically future-ready for hybrid hardware-software RF environments. DiFi defines a three-plane model: the data plane, control plane, and the time plane. On the data plane, it defines a compact packet format where raw IQ data is carried along with metadata such as streams IDs, timestamps, and sample counters. This structure basically allows receivers to maintain alignment and reconstruction accuracy. Going a little bit further, the control plane governs how endpoints negotiate capabilities, such as supported sampling rates, stream types, and bit depths, basically facilitating stream recovery, discovery, and lifecycle management. The time plane integrates support for clock distribution and synchronization, often leveraging PTP to align the sample clocks across the distributed system. This architecture basically enables the true time deterministic behavior over networks that are traditionally asynchronous and unpredictable. The DiFi standard is under active development as we speak, and each version has introduced substantial capabilities. Version 1.0 laid the groundwork with basic packet structure and stream configuration. Version 1.1 expanded support for concurrent streams, allowing multiple logical links over a shared interface, and introduced improvements to stream metadata definitions. The upcoming 1.2.1, expected to be validated soon, introduces features specifically aimed at production scalability, quality of service controls to support bandwidth prioritization, enhanced metadata descriptors to describe signals format and stream purposes more granularly, and define synchronization methods to improve alignment under bursty network conditions. These improvements are especially relevant for test setups that need to emulate real-world RF behavior with precision and repeatability. In modern satellite and aerospace projects, testing environments must mirror operational complexity, which increasingly involves cloud-based signal processing, disaggregated payloads, and, of course, hybrid vendor ecosystems. DiFi brings order to this complexity by introducing a common interface for RF signal exchange, allowing systems and subsystems to interact without vendor lock-in or bespoke protocol adaptation. This enables modular testbeds where components can be swapped and validated independently. Additionally, because DiFi control and timing planes are machine-readable and deterministic, of course, they can be embedded into automated test orchestration tools and CI/CD workflows. This basically opening the door to test automation at the RF level, which is a key enabler for iterative design cycles and scalable validation. Let's look at how DiFi manifests in practical engineering workflows. One common scenario is modem validation, where a DiFi-compliant channel emulator is inserted between a digital baseband processor and the modem under test, eliminating the need for analog cabling or format converters. In loopback emulation, DiFi allows test systems to simulate closed RF paths between transmit and receive chains entirely in the digital domain. In benchmarking, DiFi's standardized interface allows performance comparisons across different vendor devices under identical impairment conditions. And finally, for distributed testbeds, DiFi enables remote lab infrastructure where SDRs, modems, and emulators are hosted in different physical locations or cloud environments, all synchronized and orchestrated over IP. Celeos, our software-defined channel emulator, is designed to integrate seamlessly with DiFi. Its architecture already supports low-latency streaming of IQ data, precise timing alignment, and dynamic control of impairment profiles. With the planned support for DiFi 1.2.1 in our end-of-year release, Celeos will act as a DiFi node capable of transmitting and receiving sample-accurate digital intermediate frequency streams natively. It will support multiple roles, such as a source of impairment for receiver testing, as a transparent pass-through with delay injection, as a active test endpoint in a DiFi-driven validation chain, and so on and so forth. This turns basically Celeos into a key building block for any digital intermediate frequency-based testbed architecture. The next 12 months will be pivotal for DiFi adoption. As version 1.2.1 approaches finalization, we expect increasing adoption across equipment vendors, test labs, and system integrators. Our recommendation to engineering teams is to begin aligning with the standards now, building support into design, enabling early test scenarios, and contributing to interoperability efforts. At Lasting Software, we are fully committed to this vision. Celeos will continue to evolve as a reference platform for DiFi testing, and we welcome early access partners to help shape and validate the roadmap as we move toward full integration. And today, we are not just talking the talk, we're walking the walk. We are close to having a commercial release for a fully embedded DeFi support within a testbed, unlocking the ability to operate entire digital RF chains, a complete end-to-end setup with digital front ends. Henceforth, we're talking about a real-time, over-the-air, end-to-end NTN setup driven entirely by software and DeFi, all in one PC. At Lasting Software, we are proud to be an active member of the DeFi consortium, contributing to the advancement of open digital IF standards that are reshaping the future of satellite communications. Our involvement aligns with the strategic direction of both US Department of Defense initiatives and global commercial adoption goals, where interoperability, flexibility, and standardization are key. Celeos was designed with an interoperability-first mindset. It integrates seamlessly with DeFi-compliant hardware and software, allowing vendors to develop and deploy fully virtualized and vendor-agnostic testbeds. We are also contributing to the evolution of the DeFi 1.2.1 specification, with full support expected in the next major release of Celeos. This ensures we stay at the leading edge of capability while remaining closely aligned with the standards roadmap. Ultimately, our goal is to enable complete, fully digital end-to-end testbeds, as mentioned before as well, covering multiple orbital configurations, signal chains, and dynamic scenarios entirely through software-defined, DeFi-enabled architectures. So, this being said, I hope this session has shown you that high-performance digital satellite interfacing doesn't need proprietary boxes or inflexible lab environments. With Celeos and DeFi, you gain a future-proof software-defined solution built to scale with your 5G and 6G NTN ambitions. That being said, stay tuned for more sessions and product updates from Lasting Software. And if you have any questions or feedback, we'd love to hear from you. Thank you for your time and attention. Until next time, bye.